Good morning, student. In previous lecture of solid state, we had started discussion about the defect in crystalline solid. In that, we had seen that crystalline solids have three different type of defect, that is point defect, line defect, and plane defect. We had seen that out of these three defects, only one point defect is included in syllabus. And then we had started discussion about point defect in detail. In point defect also, we had seen that there are three type of different point defect. One is stoichiometric defect, second one is impurity defect, and third one is non-stoichiometric defect. Out of these three, we had started discussion about the first defect, that is stoichiometric defect, and we had seen there are four type of different stoichiometric defects. All the four we had discussed last time, that is first vacancy defect, second self-interstitial defect, third that is Schottky defect, and fourth Frankel defect. Now in this lecture, first we will go for the comparative study of Schottky and Frankel defect because it was asked in board examination, and then we will go for the discussion about the next defect, that is impurity defect. So as we know that Schottky defect, it is a vacancy defect which is generated due to the absence of equal number of cation and anion from their lattice points or lattice sites. While Frankel defect, it is an interstitial defect or dislocation defect which is generated or produced when smaller ion leave its lattice point or actual position and get accommodated in interstitial voids. Okay. Generally, cation is smaller in size in compared to anion, so that's why generally cation is dislocated from the normal site and accommodate in interstitial site. So we had seen that it is a defect which is a combination of vacancy defect and interstitial defect. Then Schottky defect is generally observed in ionic substances. Frankel defect is also in ionic substances, but Schottky defect is observed in those ionic substances where the size of cation and anion is almost same. Comparable size. Cation and anion both are of comparable size or similar size. While Frankel defect is observed in those particular ionic crystalline solids in which there is large difference in the size of cation and anion. Cations are much more smaller in compared to the size of anion. Okay. Then in Schottky defect, because we had seen that the equal number of cation and anion are missing from their place in crystalline solid, that's why due to decrease in number of ions, mass decreases, volume remains same, so density decreases. So in Schottky defect, density decreases. While in Frankel defect, because the number of atoms or ions, we can say the number of ions are same, they are not leaving the crystal lattice, only dislocation is taking place. That's why mass doesn't change, that's mass remain unaltered, volume is unaltered, so density will also be same. So due to Frankel defect, there will be no change in density. Density does not get altered. Okay. Now diagram is given over here. In Schottky defect diagram, you can see the equal number, one cation and one anion is missing from its actual lattice point. While in Frankel defect diagram, you can see the cation is missing from its lattice point, actual site, and accommodate a interstitial void. Okay, so it is a comparative study of Schottky defect and Frankel defect. It is important, it can be asked in the exam. Now we will go for discussion of next type of point defect, that is impurity defect. From name itself it is clear that this particular defect is generated due to impurity which is generated due to a foreign atom or different atom in compared to host atom. When a particular element get polluted or having impurity of different element atoms, then such type of impurity defect is generated. When a particular substance has the impurity of other elements atom, then this type of defect is generated. Suppose you are having copper metal. In copper, if there is an impurity of tin, zinc, iron, okay, so the copper metal element is not pure, it has impurity of zinc or tin or iron. So due to the presence of this impurity, the characteristics of copper will get slightly changed and a defect is generated which is due to the presence of these other element atom, and such type of defect is known as impurity defect. Is it clear? So impurity defect arise when other element atom get mixed with the host atom or a particular substance element, particular substance atoms, okay, in its crystal lattice. Okay, so impurity defect arise when foreign atom, that is atom different from the host atom, are present in crystal lattice. Again, these impurity defects are classified in two categories. Impurity defects again classified in two categories. One is substitutional impurity defect, and second one interstitial impurity defect. So first we'll go for the first category, that is substitutional impurity defect. Substitutional impurity defect, from name itself clear that particular substance atom is substituted by the atom of other element, then this type of impurity defect is generated. For this particular defect, it is compulsory that the host atoms and impurity atoms, means foreign atoms, size should be comparable. They should be of nearly similar size. Then only this substitutional impurity defect will be generated. Okay. In this defect, the foreign atoms are found at the lattice site in the place of host atom. The regular atoms are displaced from their lattice site by impurity atom. For example, if you have taken copper, in copper some of the places are substituted by, some of the copper atoms are substituted by zinc, then substitutional impurity defect is generated in copper, and result is formation of brass. An alloy of copper and zinc is generated. Similarly, copper atom, some of the copper atom are substituted by tin, then bronze, alloy of copper and tin we are getting, that is bronze. So copper and zinc, copper and tin, they are comparable in size. Okay, so whenever a particular foreign atom substitutes the original atom from its lattice sites and occupy the position, then the substitutional impurity defect is observed. Okay, so alloys are coming in this particular category, solid solutions of metal. Okay, here by diagram it will be more clear. See, the solvent metal atom are shown by green bubble and solute element atom shown by blue bubbles. So if you are taking the example of brass, so green bubbles are copper atoms and blue bubbles are zinc atoms. So zinc solute is dissolved in copper solvent and we will get brass. Or you can take the example of bronze. The green bubbles are copper atom and blue bubbles are tin atoms. So it will be the solution of tin in copper. Then also you will be getting the bronze alloy, which is a substitutional solid example of substitutional impurity defect. Okay, same another diagram you can see over here. The red bubbles showing the solvent and green bubbles showing the solute, or you can say the original metal atoms are or regular metal atoms are shown by red bubbles and foreign atoms are shown by green bubble. So it is the first substitutional impurity defect. Substitutional impurity defect, again you can see it is of two types. Okay, one, when the atoms of crystal are substituted by foreign atoms. Second, it is also generated the allovalent impurity through allovalent impurity. For example, it is known as vacancy through allovalent impurity. In this particular substitutional defect, one vacancy is created by the addition of impurity of allovalent ion. Allovalent ion means the ions which oxidation state is different than the host ion. It is generally observed in ionic solid. Suppose you have taken the crystal of sodium chloride. All cations are having unipositive charge, anions are having uninegative charge. Suppose a bivalent cation is mixed with this sodium chloride crystal. Cation, regular cation, sodium cation is univalent, while the impurity cation is bivalent. So it is a allovalent cation because its valency is different. Its valency is different than the regular cation. For example, I had mixed strontium ion with sodium chloride crystal as a impurity. So strontium chloride, if mixed with sodium chloride, then strontium ion has two positive charges, while sodium ion, host ion, has one positive charge. The oxidation state of strontium is 2+ and oxidation state of sodium is +1. So the strontium's valency is different than sodium ion, so it is a allovalent impurity. When it mixes with sodium chloride, then what happens? To maintain the electrical neutrality, when one strontium ion is coming in the crystal lattice, two sodium ions are leaving their lattice points to maintain the electrical neutrality. Okay, one strontium ion occupies the place of one sodium cation in crystal lattice while another place of sodium ion remain vacant. Okay, so two cations are replaced by one strontium cation. Out of these two cations, one cation's place is occupied by strontium while second place remain vacant. Okay, so due to the allovalent ion impurity, a vacancy is generated as well as one cation gets substituted. So that's why it is a type of substitutional impurity defect, and because of presence of allovalent cation, a vacancy is also generated. So it is a combination of substitutional as well as vacancy defect. Substitutional defect as well as vacancy defect. From diagram it will be more clear. See here, the strontium cation had occupied the place of one sodium ion while another sodium ion's place remain vacant to maintain the electrical neutrality. Okay, so in this way one strontium ion removes two sodium ions from the lattice point. So it is a combination of substitutional as well as vacancy defect. So it is a different type of substitutional impurity defect which is generally observed in ionic crystalline solids. Now next one, that is second type of impurity defect, that is interstitial impurity defect. From name itself clear, you will be getting idea that the impurity is occupying interstitial voids or interstitial space or vacant spaces in crystalline solid. That means the foreign atoms are smaller in size in compared to host atom. Then only this interstitial impurity defect is generated. Clear? For substitutional impurity defect, what is the condition? The foreign atom or the atom of other element should possess similar size to that of regular atom or actual element atom. While for impurity defect, the foreign atom, impurity atom, should be smaller in size in compared to regular atom. Okay, so in this defect, impurity atoms occupy interspecial spaces in lattice structure. Best example is steel. Steel is the alloy of iron and carbon. Iron atoms are larger in size and carbon atoms are smaller in size. So generally carbon atom occupies interstitial voids in iron crystal lattice. It will be more clear with the help of diagram. You can see over here, iron atoms are shown by gray bubbles while the carbon atoms are shown by black bubbles. Okay, so the crystal lattice is generated by iron atoms and the interstitial voids are occupied by carbon atoms or foreign atoms or impurity atoms. So in this way, due to presence of small size of impurity atoms, this interstitial impurity defect is produced. It will also generate a different type of properties, physical and chemical properties in the crystal lattice. Clear? So it is a second category of defect, that is impurity defect, substitutional defect, then second one interstitial impurity defect. So here we had completed discussion about the second category of point defect. Now last or third category of defects, point defects. What is that? Non-stoichiometric defects. See, from name itself clear, the defects in which the ratio of number of atoms, the ratio of number of constituent atoms is change, is not same as represented or shown in its chemical formula. Clear? Vernacular medium, जैसे for example मैग्नीशियम ऑक्साइड और निकल ऑक्साइड, रेशो क्या है? 1:1 है, ठीक है। पर अगर ये रेशो चेंज हो जाता है किसी भी इम्प्योरिटी के कारण, रेशो 1:1 नहीं रहता है, जो उसका स्टोकियोमेट्रिक रेशो है, एटम्स का रेशो है, वो चेंज हो जाता है, तो जो डिफेक्ट जनरेट होगा वो क्या कहलाएगा? नॉन स्टोकियोमेट्रिक डिफेक्ट। ओके, सो नॉन स्टोकियोमेट्रिक डिफेक्ट आर अराइज व्हेन रेशो ऑफ number of atoms of one kind to that of other kind, or the ratio of number of cations to anion becomes different from the indicated by its chemical formula. That is, in short, we can say stoichiometry of the compound is change. It also, you have to keep in mind that change in stoichiometry does not cause any change in crystal structure. Though stoichiometric change, ratio is change, but the crystal structure remain same. It is not going to be change. Its geometry is not going to change. Okay, regular pattern will remain as it is. So though the stoichiometry, the ratio between the constituent atoms of different elements, or the ratio between the cations and anions is going to be changed due to this defect, but the crystal structure remain same. It is not going to be changed. So again, this non-stoichiometric defect is also classified in two categories: metal deficiency defect and metal excess defect. Clear? So as we had started discussion about the non-stoichiometric defect, that there are two type of non-stoichiometric defect. Out of them, first is metal deficiency defect. So from name itself it is clear that there is the deficiency of metal. Okay, a metal ion is absent from its regular lattice point or regular site, lattice site, and then this particular defect is generated. So this defect is possible only in compound of metal, not other. Okay, and that is also showing variable oxidation state. Generally, variable oxidation state is shown by transition metal elements. So metal deficiency defect generally observed in the transition metals crystalline solids or transition metal crystals, okay, which are having the variable oxidation state. In some of the crystals, the positive metal ion missing from its regular lattice site or regular lattice point, and then to maintain the electrical neutrality, the cation of same metal element with higher oxidation state occupies the place in lattice site. For example, copper has two oxidation states, Cu2 plus, Cu1 plus, cuprous ion and cupric ion. So suppose a crystal is generated by cuprous ion and one cuprous ion is missing from its lattice point. So somewhere else in the lattice point a position is occupied by the cupric ion, Cu2 plus ion, so that the electrical neutrality of the crystal is maintained, which is may be disturbed by the absence of one cation, but because one positive charge is reduced, but at the same time due to presence of two positive charge copper ion, that positive charge is balanced, means negative one extra negative charge is balanced. So whenever a particular cation is missing from its place, then somewhere in the crystal the higher oxidation state same metal ion is present, which maintains the electrical neutrality of crystal. Okay, so in some particular transition metal crystals, okay, in this way the defect is generated. Okay, extra negative charge will be balanced by the presence of cation of the same metal with higher oxidation state than that of missing cation. It will be more clear with the help of diagram. See here, A plus ion is the regular cation which is participating in the formation of crystal lattice. At one place this cation is missing, so another place, the place is occupied by higher oxidation state cation A2 plus ion, which balance the positive charge of absence cation. Here we can take the example of cuprous and cupric ion. Okay, one cuprous ion is missing, another place a cupric ion is present, which balances one positive charge. Or you can take the example of iron, which is showing oxidation state Fe2 plus, Fe3 plus. Ferrous ion, ferric ion. There are so many transition metal elements which show the oxidation state more than one variable oxidation state. Okay, another example we are taking of ferric oxide. Okay, oxide of iron. Here you can see the regular ion which is participating in the formation of FeO is Fe2 plus ion. Some of the places this Fe2 plus ion is missing. Okay, see, you can see over here vacant spaces are shown, vacancies are shown by small square. So some places in the crystal was occupied, it is occupied by black bubble, that is representing Fe3 plus ion. So two Fe2 plus ions are missing, that means 4 positive charges are less in the crystal lattice. So 4 Fe3 plus ion are present already in crystalline solid. So these 4 extra positive charges, okay, four Fe3 plus ion means 4 extra positive charges are there, which balances the 4 positive charges which are lacking due to absence of 2 Fe2 positive ions. So in this way electrical neutrality is maintained, okay, in this metal deficiency defect by the substitution of the cation of same metal element with higher oxidation state. So it is first type of non-stoichiometric defect, that is metal deficiency defect. Second one, that is the metal excess defect. Second category is metal excess defect. From name itself clear, that is some excess metal atoms are present in the crystal lattice, and due to which this defect is produced. Okay, so again metal excess defect is also of two types. Okay, first, that is the defect which is produced due to presence of a neutral atom or an extra positive ion in interstitial void. Okay, a neutral atom or an extra positive ion occupies interstitial position. Example is zinc oxide. Okay, so first example we will observe the defect which is generated due to presence of extra neutral zinc atom present in interstitial void in zinc oxide crystal. Okay, so in diagram you can see the zinc oxide crystal is generated by the combination of Zn2 positive ion and O2 minus ion. One excess neutral atom, zinc atom, is present in interstitial void, and due to that this particular defect is generated. Okay, so due to presence of extra neutral atom of same metal element, this defect is generated. Obviously, if extra metal atom is present, then volume is same but mass is increased. So due to this particular type of metal excess defect, the density of crystalline solid will increase. So it is a consequence of this metal excess defect that density will increase. Second one, what is that? The extra positive ion, the defect which is generated due to presence of extra positive ion. Now suppose I am heating this zinc oxide crystal. So what happens? Zinc oxide get decomposed into Zn2 plus ion and oxygen atom, half O2, and 2 electrons are released. Okay, this particular Zn2 plus ion, okay, trapped into the interstitial voids, and those extra electrons are also trapped in interstitial voids. Okay, so due to that, what happened? The metal excess defect is generated. Okay, the excess cation occupies interstitial void, electrons also released are occupying interstitial voids. Okay, so in this way excess metal ion occupies interstitial void, and due to this particular defect is generated. Okay, zinc oxide on heating decompose into Zn2 plus ion, half O2 and 2 electron. Now this excess Zn2 plus ion trapped in interstitial site in the lattice, crystal lattice, as well as the electron also diffuse in the crystal and occupy the interstitial site. It will be more clear with the help of this diagram. You can see over here the 2 electrons are shown by green color bubbles, and zinc ion is also shown over there, okay, by black color. It is written over there. Okay, so ion as well as electron occupies the interstitial voids, and due to this defect is generated. In both the cases, whether the neutral atom is present in interstitial void or a cation is present in interstitial void, the stoichiometry of the compound is changed. Okay, the ratio should be 1:1, but due to presence of extra cation or extra neutral atom, it is, in case of zinc, it is greater than 1. So the ratio will be Zn 1 plus X is to O1. 1 plus X is to 1 ratio is there in this compound. Clear? Now the last defect in crystalline solid, that is second type of non-stoichiometric defect, which is produced due to anion vacancy. Anion vacancy. The defect which is produced due to anion vacancy is also known as color center or F center. This type of defect impart color to the colorless crystal. Okay. Now, for example, we can take this. We will discuss this particular defect with the help of sodium chloride crystal. When sodium chloride crystal is heated in presence of sodium vapor atmosphere, then sodium atoms get deposited on the surface of sodium crystal. Now what happens? These sodium atoms attract the chloride ion present in the crystal lattice towards itself. So this chloride ion diffuse to the surface of the crystal lattice. Here they react with sodium atom and form sodium chloride by losing extra electron. This extra electron occupies the vacancies generated due to absence of anion. Okay, so in this way the chloride ion diffuse to the surface, producing the vacancy on their regular site, which will be occupied by the electron lost by the chloride ion itself during the reaction with the sodium atom deposited on the surface. This electron which is released by chloride ion occupying the vacant space or vacant site generated by this chloride anion, and this particular free electron is only which occupies the anion vacancy is only known as F center or color center. Why it is known as color center? Because it is responsible to impart color, to produce color in crystal lattice. It will be more clear with the help of diagram. See, in this particular diagram you can see one anion vacancy is produced, and this vacancy is vacant space. This vacancy is fulfilled by free electron. So this particular vacant space occupied by electron is only known as F center or color center. If you see, pure sodium chloride is colorless, but if impurity is present due to anion vacancy, then it becomes yellow in color. This F center imparts color to the sodium chloride crystal. It imparts yellow color to the sodium chloride crystal. So due to presence of free electron, a color is produced in crystal lattice. That's why it is known as F center or color center. See here, number of cation is same, but number of anion is reduced. So stoichiometry of crystal is changed. In pure sodium chloride crystal, the ratio of cation and anion, sodium cation and chloride anion is 1:1. But here, due to presence of anion vacancy, due to presence of F center, due to presence of this defect, number of anion is reduced in compared to number of cation. So ratio is not 1:1. The ratio of cation is greater, the number of cation are greater than number of anions. So ratio is not 1:1 between cation and anion. but it is 1 plus x is to 1, means some extra cations are present over there. So the ratio is Na 1 plus x is to Cl1, that is 1 plus x is to 1, cation 1 plus x, anion 1, 1 plus x is to 1. In second diagram also you can see the anion vacancy is shown by red color, which is occupied by free electrons. So it free electron 1, it maintains the electrical neutrality of the crystal lattice. Second, it produces specific color in crystal lattice. This particular vacancy defect or metal excess defect due to anion vacancy is very important. In exam it can be asked for 2 marks. So you can easily explain it with the help of diagram. It is an important defect. Schottky defect, Frankel defect and anion vacancy defect or F center or color center. These 3 defects are very important. The question can be asked on these. Others also you should prepare, but these 3 are important. Now we will discuss one numerical. MCQ is there. A compound form SCP structure. What is the number of octahedral and tetrahedral word in 0.5 mole of substance? So you know very well the number of particle will be equal to number of moles into Avogadro number. Amount of compound is given 0.5 mole. So number of particle present in 0.5 mole will be equal to 0.5 into Avogadro number, that is 6.022 into 10 raised to power 23, that is equal to 3.011 into 10 raised to power 23. Number of octahedral words will be equal to number of atoms, so it will be 3.011 into 10 raised to power 23. Tetrahedral words are double the number of atoms, so 2 into 3.011 into 10 raised to power 23, so it is 6.022 into 10 raised to power 23. So number of tetrahedral word in 0.5 mole of substance is 3.011 into 10 raised to power 23, and number of octahedral words in 0.5 mole of substance will be 3.011 into 10 raised to power 23, and number of tetrahedral words in 0.5 mole of substance will be 6.022 into 10 raised to power 23. Number of tetrahedral words 6.022 into 10 raised to power 23, number of octahedral words 3.011 into 10 raised to power 23. So here we had completed all the topics, discussion about all the topics of chapter 1 solid state. We had discussed different type of numericals also. So here this first chapter solid state is completed. In next lecture we will start our next chapter, that is coordination chemistry or coordination compounds. Okay, thank you.